In this video in section 13.4, we're going to go ahead and look at question number 2. This problem says that the temperature T at a point UV on a metal plate is given by the function T of UV is equal to the ratio of U minus V and U plus V there. Compute the partial derivative T sub V at 4,2 and interpret your answer. Assume temperature is measured in degrees Celsius and distances are measured in meters. Okay, so one comment just to begin, when I see that subscript with the V, what we said in the last video there is that that subscript is telling us to differentiate our temperature function T with respect to V, and then we're going to evaluate that derivative at the point 4,2. Okay, so here is our setup above, right? And if I'm at, say, the location UV in my metal plate, the temperature at that location is just given by my temperature function. Okay, so let's go ahead and start by just taking the derivative of our temperature function with respect to V. Okay, so I'm going to, over here, compute TV, and if I'm going to differentiate this function with respect to V, that means I'm going to hold U constant. And notice since I have a quotient here, right, I'm going to apply the quotient rule from Calc 1. And so that's going to look like the following. So I'm going to take the derivative of the high function over the low function, right? So I'm going to do low, which is U plus V, d high, so the derivative of the numerator there with respect to V would be, in this case, a -1, minus high, that's the numerator, U minus V, d low, the derivative of the denominator with respect to V would just be 1, and then I'm going to divide by the square of what's below, right? In other words, U plus V quantity squared. Okay, great. So let's go ahead and clean this up a little bit. So here I'm going to get a negative U, and then I have a negative U there, so that's going to give me a minus 2U. And then for the V's, I'm going to get a minus V there, but then I'm going to get a minus. So in other words, a plus V there. So these V's will actually cancel out, and that's going to leave me with just U plus V quantity squared in the denominator. Okay, so this is my V derivative of my temperature function. And now what I want to do is evaluate that at our particular point, which is 4,2. Okay, so again, just remember this is saying here, this is U and this is V. So we're going to just plug in 4 for U, and then down in the denominator I'm going to get a 4 plus a 2 quantity squared, right? So this is what? Minus 8 divided by, and this is 6 squared, so that's 36. Okay, so go ahead and divide by 4, so you got minus 2/9. Okay, great. Well, that is the derivative, but now let's go ahead and interpret what exactly this is saying. Okay, so over here in the picture, let's say here's the point 4,2, and let's just say that this direction here would be the U direction, and this direction here would be the V direction. Okay, so one thing to note here is that the temperature at the point 4,2, so T of 0.42, well, is what? I'll just plug this into my temperature equation. So I'll do 4 minus 2 for the numerator, and I'm just going to get 2 there. And then that'd be 4 plus 2 in the denominator, that'd be 6. 2/6 is 1/3, and this would be degrees Celsius. Okay, so at this particular location, the temperature is 1/3 of a degree Celsius, so pretty darn, pretty much freezing. And then, since I see that the v derivative of my temperature function is a -2/9, what that's telling me is that if I move in the v direction, my temperature will be decreasing at this rate, right? At least, right, in an instantaneous sense, leaving this point for 2, okay? So putting that all together, what I can conclude here is that at the point 4,2, the temperature is decreasing at a rate of -2/9 degrees Celsius per meter, because notice temperature is measured in Celsius and distances are measured in meters. And that rate is happening, right, if I move in the positive v direction. So if I move, say, vertically up, I'm going to be cooling down, at least in an instantaneous sense, at that point. Okay, so great, that's going to do it for this problem.